Hello there, I'm Cristina Elisa Martina, I'm a postdoc in Meiler Lab, and today I will do the walkthrough tutorial for the Glycan modeling portion of this workshop. You should start having the instruction file, a terminal Windows. You should be able to access PyMol from your workstation in order to visualize the PDB. And first thing, we start from the folder of the tutorial. So if we check what we have now in the folder, we have just the instruction file, input file, folder, and output file. As usual for the tutorial, we will create our own working directory. So we will do make dir work dir, and then we will cd in work dir, and there should be nothing inside. So this is really setting up the system. Now, in the first portion of this tutorial, we will download, trim, clean, and score the complex in the PDB 2J88. You have the instruction to both or download the PDB from PDB, or you can copy from the folder input file that we give. I will just copy to be quick. So now in the folder we should have this PDB. The next step is checking this protein with PyMol. So we will open it with PyMol. If you can open PyMol directly by the terminal, this will be great. It will be also easier to save the molecule, but if you cannot, remember that you can always just open PyMol as you can do, and then drag the molecule that you are interested inside the black windows. So let's open PyMol. Okay, here we have the 2J88 PDB. So we will remove the solvent. I will use the command line, but you can do also in the manual way. And then we will color by chain. That will make it slightly easier to understand what are the different chains present in this PDB. So you can see now in green we have the B hyaluronidase, and in cyan and magenta we have the antibody. And the immunogenic site that we are going to mask is exactly this portion here of the hyaluronidase. As you can see in the antibody portion here, we have many missing residues. So we are missing residues in here, we are missing residues in here, also in this chain. And you can see that this portion of the antibody is not well resolved. So in order to make the calculation quicker, we will just remove it. And you can manually select the residues that we want to remove. I already counted them for you, so you can simply run this command, select, we give a name for the selection that will be to remove, and then we say in chain H, we remove from 111 to 180, while from chain L, we will remove from 107 to 205. So with this command, we select this portion that will be called to remove, and you can select the select easily in there. And now we will remove with the remove command. Here it is. So now we have a shorter version of the antibody still binding the antigen, and we will say this molecule. So we use save 2J88 trim.pdb. This will work if you can open your PyMol windows from the terminal inside the folder you are working. If this is not working for you, you can easily go File, Export Molecule, and follow the next windows. You should be able to do it. Okay, let's save it. And now let's check if we have it in our folder. Okay, so we close PyMol, we are at step 8. We check if we saved our file. So you can see we have the original one, download from the protein data bank, and this one is the trimmed version that we just created. So now we go with step 9, we need to clean the PDB, and we will use a tool within Rosetta. Is a Python script that was created, and that will basically renumber the chain and remove any extra atom. Like we remove all the water, we already did it, but we remove, for example, salt if present, and so on. So here is the command. As you can see, we have these 3 files that are created, that are the FASTA sequence for each chain. So if now we check what we have in the folder, we have the original PDB, we have the FASTA for chain A, FASTA for chain H, and FASTA for chain L. We have the trim PDB that we created before, and we have the clean version of it, that is this one. If now we check the PyMol for all the PDB we have in the folder, we should get something like this. So we have the original one is 2J88, then we have the trim version and the clean version, so the structure is exactly the same, but what is changed is the sequence. So you can see here that our clean version is renumbered from 1, and it go up to 536, 37, while in the previous structure the antibody chain was restarting from 1 for both H and L. Okay, we are now going to score this interface. So we are calculating the binding energy between the antibody and the antigen. For doing so, we will need to copy the file for the interface analyzer mover. That now should be in the folder. So we have both the XML and the option. You should have already covered these files in the protein-protein docking tutorial. So let's go directly to run this command. It will take more or less 1 minute. Okay, so after the interface analyzer mover finish, we should have a score file. That is this one. And if we open it, you can see the classic score file from Rosetta. So we have multiple columns. The one that we are interested in are the total score in column 2. The DG separated, that is the indication for the binding energy between the antigen and the antibody. This is column 6. And then we will need the SC value that I need to find in here is here. That is in column 36. The SC value is for shape complementarity. So we are trying to check how good the shape of the antigen is relative to the shape of the antibody. A value of 1, it means that they have a perfect fit. So the antigen completely fit well the antibody, and we usually consider a value of 0.65 the cutoff limit for considering good fitting or bad fitting. So over 0.65 is a good fitting, lower than 0.65 is not an optimal fitting. Now, from the score file, we will extract just these few information. So with this command, this is an awk command. You can do it manually through Excel, extracting the column, or if you are more comfortable with the terminal, you can just use this command. So we have a new file now that is these 0 clean scores, and here is the file. So we will have the total score that is -64. This is not a good score for the proteins of this size, 500 amino acid. We will expect at least -1500. The DG separated is 48 Rosetta energy unit. This is a positive value, and this means it's not good for us. We are expecting something negative, and in particular an antibody has an average energy of -50 Rosetta energy unit in binding. There are some that are weaker binders, so we can have -30. There are some that can be strong binder, and I saw values of -70, but this is definitely something we need to improve. And the reason is that this structure was scored starting from the crystal structure that is not optimal for using Rosetta, so we will need to relax and then rescore this PDB. Okay, we are now starting the point 2 of our tutorial, the relax and score again. For relax, we will use fast relax, and we will copy the XML and option file. So now you can see that we have these 2 files in our working folder. I will start running the command. It will take more or less 1 hour, so I will come back to you once it is finished. Okay, after 1 hour the relax finish, as you can see here. Now we need to rescore the structure. We will use interface analyzer as we did before. I'm running it right away. It will again take more or less 1 minute, so we are in step 3. here, and then again we will take the relax score that we obtain from the interface analyzer and extract the column of interest, so we can then compare the energies after relax. Okay, it finished. So if you now check what we have in the folder, we have, this is the PDB after relax. We ask only for one output, but usually you should ask for at least 10 and then select the best one before going on with the next step. But for time reason, we will just produce one in this tutorial. And then we have the relax score. So I will create the other file that is the relax score in here, and we can see the result in here. So we have the relax PDB. Now this total score in column 2 is minus 1656. You may have slightly different result because Rosetta is based on random sampling, so all the run that you may do with relax may give you different scores, but for sure you will see that the results are much different than before. So if we compare now, this is the relax and this is the score pre-relax, we pass from minus 60 something to minus 1600. And the same for the DG separated, we pass from positive 48 to minus 43. So this is a very good value for antibody binding. Now we will check the structures with PyMol. Okay, here are the two structures. We have in green the original structure, download from PDB and clean, so before relax, and in cyan we have the post-relax. You can see that we have a slightly different position, especially for the antibody, so there was a rearrangement in the protein due to relax, but this is overall not significant. Now, the next step, we will check which residues. I'm sorry, this is my dog. Okay, now we have to understand where is the binding site between the antigen and the antibody. I will remove the unrefined structure and I will color by chain. Oops. Okay, here it is. So you can see that the main contact region is in this loop. You can select the residues and see which number they are by here, so you can do something like this. Or I already counted them for you, so you can create, as we did before, a selection that we will call interface. And now this is selected, and then we will show in sticks. So you can now see the residues that are in there. And then, to make it more clear, we will color in red just to have more contrast. Okay, here it is. So the residues that are actually involved in the binding, I will say that are 129. So this phenylalanine, 130 and 131. So these are the ones that we may consider for inserting a glycan chain in order to block this full epitope. And for time reason, we will test only one of these 3 amino acids. We will test number 129. But in a normal situation or in a normal experiment, you should test all of them. So let's now pass to the next step, that is step number 3. In step number 3, we will have to insert the sequon. So we are at page 4, insert the sequon to add the glycosylation site. In the video introduction, I mentioned and explained what a sequon is a triplet of amino acid. The first has to be an asparagine, and this will be the amino acid that will be glycosylated. The second can be anything except of a proline, and the third one can be both a threonine or a serine. So we will use 2 different ways within Rosetta to insert this motif. One is designed to be specific for inserting glycan sequence, so it's very specific for this kind of tutorial. The second is a more general approach that you can use to insert any motif that doesn't need to be the sequon for glycosylation, can be any motif that you are interested in or you are working in, and you can easily insert it in the protein. So before starting with inserting the sequon, we will need to remove the antibody. So since now on, we will work only with the antigen, with the B hyaluronidase. And to remove the antibody, we will use the delete chain mover. So I'm going to copy the XML in the folder. We have it in here, delete chain, and I can show you how it looks like. Here it is. So what is basically doing is you write in here the name of the chain that you want to remove, and they will be removed from the PDB. Very straightforward, nothing fancy in here. So let's remove it. It will take really a few seconds, and then we will check with Pymol the PDB. We will also rename the PDB, because since we are doing multiple steps one after the other, now if we check, we have a new file that is del rlx, the PDB name, and so on. So you can see that our name becomes quite long. So just to short the name, we will rename it, but this is not a necessary step. If you are working on your own, you can keep your original name, and you can basically see all the steps that were done. So we start from the PDB, and then we relax, we delete the chain, and so on. So let me Pymol. Okay, here is the structure that we obtained. So we have only chain A, that is the B hyaluronidase, and we don't have the antibody anymore. So let's close it, and now we pass to the next step, that is number 4. So we will rename it. And then we will copy the file for the first way to insert the glycan, the one that is more official for glycosylation. And this mover is not just working with N glycosylation, you can also insert C glycosylation. So the sequon for the C glycosylation type is already integrated in Rosetta, so can be used for both. So here we are copying the create glycan sequon. The XML is this one. We are writing in here the amino acid where we will have the glycosylation, so the asparagine, and end will be the third position. So the motif will go from the amino acid 129 to 131. This will be defined in the command line. Then we have some simple metric here that we will run before. So we will have pre-matrix, the motif creator mover, and then afterwards. And we will check both the total energy, the surface area, solvent accessible surface area, and then the sequence. The motif creator is in here, so this is creates glycan sequon mover, and then after we will run the postmetric. Okay, let's run it. It should take again very quickly. And I did something wrong. I forgot a dash. So we define you can see it in here in the command line, we define the start 129 residues on the chain A, and the end is 131. This is where the sequon will be. So as you see, it already finished, and now we should have a new file that is sequon1, and we are now going to see it with Pymol. Okay, here we have two structures. You cannot see the second one because they are matching exactly. So here are both. What we are really interested in is analyzing the interface. So we will use again the command to select something that is in here. We will show the stick, and we will also set the sequence view so we can check the residues. And if you check in here, so our original was phenylalanine in position 29, and now is an asparagine. The middle residues remain the same. It was not a proline, so it's good for the sequon. And the third residue was a D, and now we change it to a serine. So you can see here how it changed. Okay, we are at step 8, so we close PyMol, and now we will use the second method to insert a motif. It's not bound to glycans, can be any motif that you want to insert. And we will need first to copy the XML, so I will do it quickly, so I'll show you then. The XML is this one. It's very similar to the one that I had before, so again here we have a residue selector. We will select the amino acid 129 on chain A. Here we'll define the end of the motifs as amino acid 131. We have the simple metric, and what it changes now, we have this create sequence motif mover, in which we define the motif that is this one. So the motif will be in the first position, we want an asparagine. In the middle position, we want the same amino acid that originally was in there. And then in this case, we will add a threonine. So before we had a serine, now we will add a threonine. And then we will have, as before, the pre-matrix and the post-matrix. Now, let me re-put this as it was. We save it, we close it, and we are ready to run it. And again, here in the command line, you can see that I define the start and the end. And here we have a different prefix, so we can distinguish the two PDB. Again, it should take really quickly as before. It's finished right now. And if we now check what is in the folder, we can find that we have a second PDB file that is sequon2 and a second score. So I didn't mention and I didn't open before the score. I will do it now so we can compare the two. But first, let's check these. We will check both structure on PyMol. Okay, we are on PyMol. Again, we can see only one structure, but we actually have 3 in there. So the first one is the original one, the wild type without sequon. Then we have the sequon one that we designed before and sequon 2 that we design now. So I will again select the interface and show the sticks. And set the sequence view so we can see the differences. So again, the first one is the original. The second is sequon 1, and the third is sequon 2. So you can see that now we have both sequon for N-glycosylation, NXS, and NXT. And you can see here how they change. Okay, let's now analyze both score files. So if we do ls, we create one score file for the first sequon and another one for the second sequon, and we will analyze them both together. So this first command that I'm running will just put the name of the columns, so it's basically the header. And then we will use this command to extract the information from the score 1, and this one to extract the information from the score 2. So here we are at this level, point 13. So what we are doing is extracting the PDB name, that is always the last column, the motif sequence that we inserted, this will be column 26, the total energy post and pre-sequon, that are columns 19 and 21, and the SASA post and pre-sequon, 18 and 20, and we will directly calculate the delta, so model minus native value, using awk. So if you can see in here, we are selecting the last column with NF, column 26, 19 and 21, and then we will plot here the delta 19 minus 21. And the same here, we will have the delta for the SASA. So let's now check this file. you can see this is the first command we gave to add the header. And then here we have the two values. So the total energy before is this one, after is this one. So you can see that we have very similar energy. We are not changing or making the protein less stable. Here is the difference. So for sequon 2, the energy is exactly the same. We are slightly improving the energy with sequon 1. And the SASA, so the solvent accessible surface area, you can see that is in both cases we decrease the exposed area because we are negative. If this was a positive value, it means that we add something, add a bigger amino acid compared to the one that was before. But since we remove a phenylalanine, it's easy to go down with the solvent accessible surface area. Okay. So both methods, they didn't give big difference. There may be cases where if you remove one key residue in the interaction, you can see that the model will be worse than the wild type. And in this case, you may be careful in modifying that position. So this is not the case for this position, but be aware that you can disrupt the stability of the protein by removing an amino acid to insert the sequon. Okay, let's remove this. We are now starting section 4, so the actual moment in which we will model a glycan, insert it in the PDB, and then find the lowest energy conformation for the glycan itself. So let's clear these. And let's start copying the input file that we need. So you can find in here, we have, I'm lost, the glycosylate here, XML, and the option file. So if we open the glycosylate, XML, this is what you will see. Again, we are using residue selector to select the residues that we want to glycosylate. That will be 129, the asparagine residue we just designed. Then we will use simple matrix again, pre and post glycosylation to check the energy and the SASA. And then this is the simple glycosylate mover that will add the actual glycosylation in the PDB. So here you can see that the glycosylation that we want to add is a MAN5. You can find the information about this sugar in the database of Rosetta. So if you go database, chemicals, carbohydrates, and so on, you should find a folder with all the sugars and glycans that are now already integrated in Rosetta. Okay, so once we move the glycosylate, we can start and run it. Here, again, we define the starting, that is the one that will be glycosylated. It should take very quickly, 1 minute, and then afterwards we will open PyMol and analyze both the original without glycosylation and the glycosylated structure. I didn't mention before, we designed two different sequons. One was NXS and the second was NXT. The score that we obtained in the previous step, number 3, were very similar, so both are equally good, but there are evidence that experimentally the NXT sequon is more efficient, so the glycosylation is present most of the time, while sometimes for the sequon NXS, this is not the case. So between the two, we choose sequon 2, and this was my input structure. I didn't mention it, but you can see in here that the input is sequon 2. Okay, let's go with PyMol. Here are the two structures. So the green one is the original one without the glycosylation, and this one is the one with glycosylation. Now you cannot see the connection in here because we are not showing the sticks of the side chains, but now we will do it really quickly. So we will select residue 129, and then we'll do show sticks. So you can see now the connection in here between the protein and the glycan. So the glycan that we have here is not in its optimal conformation. So this was just roughly added to the structure, and as we will see in a moment, the energy is really bad because the glycan conformation is not optimal. So we will now, in the next step, model it in order to reach more stable conformation and a better score for this glycosylated protein. Okay, before modeling the glycan, we will check the actual score that we got after glycosylation. So we will run like this. We should have this new file that is glycosylation score that I'm showing you here. So here I'm reporting only the post-total energy and the post-SASA, so you can see that we have a positive 5,000 and more Rosetta energy unit energy, and this is definitely a score that we don't want. Like, this is a very bad score in Rosetta, in the Rosetta world. Okay, so let me clear this. Now the next step will be to model, and to model we first need, of course, the XML file and the option file. So if we list, now we have two files that are model glycan option and model glycan XML. Let me see if I can find the model XML. Here it is. Again, it's very similar. We have the total matrix and so on, but we will use this glycan tree modeler in order to model, and we will do 5 rounds and so on. So again, we will calculate pre-matrix and post-matrix. Now let's run it. This will take a while. We will ask 10 different models as output, and in my computer it will take 2 hours. So if you have the time that you can wait, just run it, and when it finishes, you come back and you analyze the structure. If you do not have the time, you can go in output structure and just copy the models. They are prepared in there. So let me run this and see you in a couple of hours. Okay, so after more or less 2 hours on my computer, we created 10 output file. You can see here are the 10 model glycan. We have also the score. So we will first analyze the score with, again, we extract the data from the score file, and here it is. So you can see we reach reasonable energies. Before we were minus 1,800, minus 1,600, but remember that we remove the antibodies. So now we are scoring just the antigen. And you can see that all of them have fairly similar result. We are around minus 860. That is definitely acceptable for the protein. And now let's check them with PyMon. Okay, here are the 10 structures that we just generated. You can see that we have all our glycan in different conformation, but they still score very similar one to each other. This is because glycans are extremely flexible. They can have different low energy conformations. So this is one example. Like, these are some examples. Here we model just 10 different glycan, like we model the same glycan but in 10 different conformation. When you do a real production run, you will model much more proteins. So you will go 500, I will say, is the minimum to go on with. Let's show the residue 129 so we can connect the glycan to the protein, and then we will load the original structure with the antibody to see how the glycosylation is actually blocking this immunogenic site. So the antibody is now in here, and you can see how glycans are overlapping exactly in the same space in where the antibody was following before. So if we imagine to produce this protein in a cell and then try to bind the antibody will have no access to this epitope. So here you can see how the glycans are now taking the space that was before occupied by the antibody. Okay, I hope you enjoyed this tutorial, and I hope some of you at least will decide to work with glycans, because glycans are super cool. And do not hesitate to ask questions in Discord if you have any, and let me know if you need some help. Bye!